Well, hello, Algebra 2. Here we are yet again together, and today we're going to be looking at section 6.7 and talking about polynomial equations. So we've kind of developed all the work that we needed to lead up to this, and now we're just going to be talking about what happens when a polynomial is equal to something. Therefore, it is therefore an equation. As a quick review, a warm-up activity, if we were to solve this very first problem, 4x minus 5 equals 0, we would add 5 to both sides. We would get 4x equals 5. We would then divide by that 4 from both sides, and we get that x equals 5 over 4. In the second example, notice that we have a polynomial, but this does not factor nicely. And so we're going to have to make use of the quadratic equation. Negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so if you did all of that work, you should get the answer of negative 5 plus or minus the square root of 33 over 2. All right, so if we are given something like this, where it says write an equation with the roots x equals negative 6 and 13, remember the roots are just the opposites of these signs if we're writing the binomial. So we just rewrite this as, sorry, that's the actual answer. We would write this first of all as x, the quantity x plus 6 times the quantity x minus 13. And so then as we FOIL this out, we would get x squared plus 6x minus 13x minus 78. And when we bring these two terms together, we get a minus 7, and this would be our answer. Okay, so many polynomial equations can be solved by writing the equation in its general form, p of x equals 0. So often what we're going to do, if we get stuff on both sides of the equal sign, we're going to move everything over to one side, that set it equal to 0, factor out that polynomial through a lot of the rules we learned last time in factoring polynomials, and then applying the zero product property, which just means if any part of a multiple segmented thing is multiplied together, if any part of those multiplications is a 0, when you multiply 0 by anything else, you get 0. So you set each individual part to 0, and you can solve for all the roots. So here's an example. 3x cubed minus x squared plus 27x minus 9 equals 0. Well, this guy, we're going to, probably the best way to go about this one is to realize that you can group these into a couple little groups and factor out something. In this case, the first part, we'll factor out an x squared, and we'll be left with 3x minus 1. That's on this part. And then the second part, we can, out of these guys, we can factor out a 9 and be left with 3x minus 1. Notice this works because these two guys are the same. And when they're the same, then we can set that up as 3x minus 1. And then we take the two guys that are being multiplied into this, we just add them together into their own quantity, x squared plus 9. Because that's what you end up doing, right, when you FOIL these anyway. It's just kind of bringing it this direction. So from that, we can then set both of these quantities equal to 0. We set this equal to 0 and set this equal to 0. Because if either one of these equals 0, then the whole thing equals 0. So 3x minus 1 equals 0, or x squared plus 9 equals 0. On this one, we could solve this for 3x equals 1 or x equals 1/3. The one on the right, it would be x squared equals negative 9. When we take the square root of that, we get the square root of negative 9, which would be plus or minus 3i. I, again, being the imaginary number, standing for the square root of negative 1. So we have the solutions of 1/3 and plus and minus 3i. Remember, it's always plus and minus 2 whenever you take the square root. Well, this guy, solve x cubed equals 5x minus 2. Well, as I told you before, the first thing we want to do is move everything over to the left side. So we have x cubed minus 5x plus 2 equals 0. What do we do now? Well, we say this is what p of x equals. P of x equals x cubed minus 5x plus 2. And now we just consider what the possible rational roots are. Remember, we learned last time together that just involves taking the the constant that we have at the end of the polynomial, and we look at the factors of that guy, and then we divide it by factors of the coefficient in front of the leading term of the polynomial, the one with the highest power associated. So in this case, it's just a 1 that's sitting here in front of the x cubed, and we have a positive 2 here at the end. So we just take combinations of 2 divided by 1. And remember, these can be plus or minus on both of these. So the answers are just plus and minus 1 and plus and minus 2 are the factors of 2. So let's try out 2. If we put in 2 to this polynomial, we get 2 times 2 times 2 is 8. 8 minus 2, 5 times 2 is 10. So 8 minus 10 is negative 2. Plus 2 is 0. So since we got a 0 there, remember, we know then that is a root of this equation. So x minus 2 has to be a factor. Remember, we changed the sign from this. So it goes from 2 to a negative 2 here. So x minus 2 is a factor. So that means that we can put the positive 2 into the box and do our synthetic division. Remember, here, there's a trick. This has 1. We're missing the x squared term. So we have to write that as a 0x squared and then negative 5x plus 2. So it should write 1, 0, negative 5, 2. Don't forget this 0. You have to look to make sure that you've got every power of x being represented, starting from the highest one moving downward. So remember how we do synthetic division. We bring down that first one. We then multiply this by what's in the box, so it'd be a 2. We then add down, we get 2. We multiply that by the 2 in the box, and we get 4. We add down, we get a negative 1. We multiply that by 2, we get a negative 2. We add down, we get 0, which is what we are supposed to get. That's what we determined already. Remember, then we can just work backwards from right to left. This is our constant. The next one becomes the x term. The next one becomes our x squared term. So, again, looking at this box means that we have an x minus 2 term. Remember, again, change the sign from what is over here. And then we have what's left over, x squared plus 2x minus 1. So the question is, can we factor this further? So it's either x minus 2 equals 0 or x squared plus 2x minus 1 equals 0. Well, this part doesn't factor nicely, so we're going to have to use the quadratic formula. And when you do the quadratic formula, you get negative 1 plus or minus the square root of 2. So we have 3 roots again, 3 solutions, 2, and minus 1, a negative 1 minus square root of 2, and a negative 1 plus the square root of 2. So we've got 3 answers here. So you might be able to see a pattern here whenever we're getting solutions to polynomials, and that brings us to a fundamental theorem of algebra. Every polynomial equation of positive degree n has at least one complex root. So if it has a positive degree n for the power of x, then it has at least one complex root. Corollary to this is that every polynomial equation of positive degree n has exactly n complex roots, including multiple roots. The n complex roots may be real or imaginary numbers. So again, if we have an equation where we have x to the first power, there'll be exactly one complex root. If it's x squared, then we'll have 2. If it's x cubed, we'll have 3. If it's x to the fourth, we'll have 4. And on it goes. So state the number of complex roots for 4x to the fourth minus 16x cubed plus 15x squared plus 4x minus 4. Well, all we have to do is look at the highest power of x, which is 4 here. So the answer must be 4. Since it's a degree of 4, the equation has 4 complex roots. And I'll just show you, if you plugged in 2, you would find out that x minus 2 is a factor of this. And then if you, with the remainder of that, did 2 again, you'd find that x minus 2 is another factor of this. And then that last term there, 4x squared minus 1, is a difference of squares, which could be further factored into 2x plus 1, 2x minus 1. And so we get the answer 2, negative 1/2, and positive 1/2. But this answer 2 is a double root. And so there really are still 4 roots, just so happens that one of them is a double root. And so that's why, again, this holds to be constant, The number of complex roots is still 4. It's just that one of them is a double root. Now, the irrational root theorem says if a plus the square root of b is a root of a polynomial, where that polynomial has rational coefficients, a and b are rational, and the square root of b is irrational, then its conjugate, a minus the square root of b, is also a root. So if I have an a plus square root of b, and I have rational coefficients, and a and b are rational themselves, but the square root of b is irrational, then we know that the a minus the square root of b is also a root of that equation. Similarly, by the complex root theorem, if a plus bi is a root, where p of x has real coefficients, then the conjugate a minus bi is also a root. So given the polynomial function p of x and the associated polynomial equation p of x equals 0, the following statements are all equivalent. First of all, x minus a is a factor of p of x. Secondly, a is a 0 of or root of p of x. And thirdly, a is a root of p of x equals 0. And these are all things that we've already seen together. All right, so write a polynomial function of least degree with 2 and 1 plus 5 square roots of 3 as zeros. Now this example is being set up because note here that we're given one of the situations where we have 1 plus 5 square roots of 3. Well, if that is a root, then we must also know that 1 minus the 5 square roots of 3 must also be a root, which means we can then set up the polynomial to look like this. X minus 2 times x minus this first root, 1 plus 5 square roots of 3, times x minus 1 minus the 5 square roots of 3. So we see here our several roots. So we have 2, 1 plus 5 square roots of 3, 1 minus 5 square roots of 3. Now this looks really messy, but I just want to at least show you the way in which you would go about this. You would just put whatever the roots are. Here's 2, 1 plus 5 square roots of 3, 1 minus 5 square roots of 3, and we just always write x minus those roots in each case. So x minus, x minus, x minus. Okay, now you can multiply this out. Note here, if we just rewrite this a little bit, we can remember by rules of association, we can say here x minus 1 plus 5 square roots of 3 can be rewritten as x minus 1 plus 5 square roots of 3, x minus 1 minus 5 square roots of 3. And we do that so that way when we FOIL this whole part, we get x minus 1 quantity squared, which can be rewritten as x squared minus 2x plus 1. Then this part, again, times this guy, and then this part times this guy cancel out because you have a minus and a plus times those. So we just get rid of all of that, and we just have the last term then, 5 square roots of 3 times negative 5 square roots of 3, which gives us a negative 75. And then we can combine like terms. So we get x minus 2 times the quantity x squared minus 2x minus 74. Remember, we just add these two together and get a negative 74. And now all I have to do is multiply all of this out. FOIL this guy into each and every one of these, and this guy goes into each and every one of those. And we get an answer that looks like x cubed minus 4x squared minus 70x plus 148. Okay, you'll have less problems that are like that and more like the previous problems that we've done where I've given you the polynomial and you're giving me the roots. But this just shows it in the reverse order. You can also go the other way. All right, so your assignment is in 6.7 to do numbers 2 through 30 and then numbers 42 through 50 evens. This is on pages 269 and 270 of your book. As always, if you have any questions, reach out to me. Let me know. You can re-watch through this video as many times as you need to. Also read the introduction to the chapter. They really are decent introductions and helpful. But anyway, let me know if you need any other help. Otherwise, hope you guys are doing well, and I will see you for one more video this week.